Chemsters, this is Mrs. Vandelay bringing you another edition of Chemster video, I guess. We are picking up where we left off. We've already talked about aldehydes and ketones, and as you know, my favorite organic compound is the four-membered aldehyde group. And so now we're moving on to the next functional group called carboxylic acids and esters. Remember how we did aldehydes and ketones? I call them cousins. So in the case of it's an aldehyde, so if this is my aldehyde, and then what was your ketone, you remove the H. I love my board here. Remove the H and you put another carbon in. So that was your ketone. You're going to see there's a similar relationship with carboxylic acids and esters. So let's see what's going on here. It says the taste of vinegar, the sting of fire ants, the rancid smell of butter, the relief derived from aspirin are all due to compounds that belong to the most important family of organic acids called the carboxylic acids. All right, save the best for last. The resilience of polyester and nylon fabrics, the softness of silk, the strength of bacterial cell walls, and our own cell membranes are all due to derivative of carboxylic acids called the esters. Now it says the functional group common to all carboxylic acids is the carboxyl group, which is made up of the carbonyl group and the hydroxyl group. Well, what the heck is that? So here we go. That would be, in a sense, the carboxyl group with a carbon and an oxygen. And here's the hydroxyl group, which you might recognize as the OH from when we talk about the alcohol. So remember how the alcohols had the side chain, like 2-hydroxy, whatever? That's the hydroxyl group. So this is your carbonyl group. And this is your hydroxyl group. I'll just point to that one. And put those together, and that's your carboxylic acid. You might also see this as RCOOH, and whenever you see those two O's put together like that, it is your carboxylic acid. Once in a great while, you'll see it written as this. Probably for me, Mrs. Vandelay, this is probably the most common way I will talk about carboxylic acids. So let's see here, what's next? Nomenclature. Well, this is kind of interesting because it was your carboxylic acids is where we get a lot of our common prefix names, okay? So I thought it might be interesting to see some of these. The IUPAC is probably what I will end up using most of the time, and so let's just kind of see what these are about. It says their abundance in nature, carboxylic acids are among the earliest classes of compounds studied by organic chemists, so there's a bunch of early common names. Most of them have many Latin or Greek roots. And finally, the IUPAC replaced the final E in the name of the corresponding alkane and added oic acid. So you got to count your carbons. So here we go. If I have one carbon, they actually get that from ants. Have you ever been stung by a fire ant? It really hurts. And so that acid that you get stung by is called formic acid. Well, the IUPAC name, you only have one carbon, so methane or methane, drop the E, put oic acid, methanoic acid. So if you want, you can see here COOH with another hydrogen. That's your methanoic acid. Your 2-carbon acid is your vinegar. It's your Latin. So that's where the acetic acid or the acetate came from, is actually from its Latin root because it was known for so long. Your acetic acid is your common name, and your 2 carbons, 1, 2, is your ethanoic acid. 3 carbons is found in milk. You can maybe see your protospin is your first fat is what that is, and that's where you get propionic acid. But our IUPAC, we actually just changed those letters a little bit to get propanoic acid. Butyric acid, notice our word for butter came from that, so butyric acid or butanoic acid. Let's go on and see what the next page brings. 5-carbon would be pentanoic acid. We get our valerian root, which is to be strong. So it was valeric acid. I really didn't know that. 6-carbon is goat's, Latin for caper, so caproic acid. Fortunately, we have hexanoic acid. The next one is a vine blossom, a Greek word there. I'm not really sure what that all is, but apparently this acid comes from this particular kind of vine blossom, and so we call it heptanoic acid. Notice we have goats again. Here's goats, here's goats. So they changed it just a little bit to go from hexanoic to octanoic. So I'm really glad we have the IUPAC names, because I don't know if I could keep these guys, straight in my mind. 9 is an herb with a stork shaped seeds. How's that? So that's where the common name is, but I would prefer nonanoic acid. And finally, notice number 10 again had to do with goats, believe it or not. And so here's capric acid, and again, man, there's 3 acids derived from goats. I prefer the IUPAC. So anyway, substitute acids are named 2As. The IUPAC chain is numbered at the beginning of the carboxyl carbon group, and substituents are located in the usual way. But however, if the common name is used, and the substituents are located with Greek letters beginning with the alpha carbon. Holy cow, let's not worry about it, okay? So here we have the first one, the IUPAC name is 2-bromopropanoic acid. Remember, this is always your first, okay? The common name would be bromopropanoic acid. Don't worry about that. All right. So what about over here? 1, 2, 3. That's prop. So it's propanoic acid. Why did I not number it? Well, could the double bond be right here? The answer is no way, because that would give you 5 bonds on the carbon. So it cannot be 1 propanoic acid, so it has to be just 2, or just plain old propanoic acid. There's no way you're going to get something else. With this other strange looking thing over here, which truly exists, here's my 1, 2, 3, 4, so we know it's butanoic acid, but on the third carbon is your hydroxy group, which does not take priority. The carboxylic acid takes priority, so we name it first, and then we make the alcohol side chain, the hydroxy. Anyway, it says do not mix these. Let's agree only to use the IUPAC. There's no way I can remember all those goat names and what else. So we're just going to use the IUPAC from here on out. But again, sometimes the history is kind of interesting to see. All right, what about the next page? All right, in order to name these, it says the carboxyl group has priority over alcohol, aldehyde, and ketone functional groups, okay? So we already knew that the alcohol is hydroxy. How do I deal with this just cetyl bond O? Okay, like what we'd find out in an aldehyde and a ketone. So if I look at this functional group, this is your carboxylic acid, all right, Ca here, and over here is your aldehyde. So the carboxylic acid takes priority over really everything. So what happens if you have an aldehyde or a ketone and a carboxylic acid? How do I use that? Well, we use this prefix oxo, okay? So that is my side chain now. The oxygen is my side chain. So I'm going to erase this. Let's figure out how this is. This is my number 1 carbon always. So something's on my third carbon. So it is 3 is just a double bond O, which is your oxo. So your C double bond O is your oxo. And now I have 3 carbons. So it's they're all single bond, and oic acid. Now over here, what else do you notice? Here's my carboxylic acid, all right, Ca. Here's my ketone. I also have a bromine in all this. 1, 2, 3, 4, 5. So what takes priority? What are named first? This is alphabetical. So you know it's going to end in oic acid, but your bromo is going to come first. So 2 bromo. 4 oxo. Again, that's just C double bond O is oxo, and now we have pentanoic acid. Okay. How about the next one down? If I can get there. There we go. When the carboxyl group is attached to a ring, the ending of carboxylic acid is used to name the parent cycloalkane. So here we go. So this is my parent. So in a sense, the cyclo now takes priority, but the ending will be totally carboxylic acid. So this is my carboxylic acid. This is my cyclo. So watch how this is named. This is called cyclopentane carboxylic acid. Oops, only 1 L. Sorry about that. Boop. There we go. Okay. And what about over here? Okay. Notice how I have two chains. I have the carboxylic acid and I have a chlorine. So how am I working this? Notice the hydrogens are trans, so the chlorine and the carboxylic acid are also trans. So it's trans 3-chloro cyclobutane carboxylic acid. There we go. Okay. What about the next one? Oops, I almost got that. So now what? Aromatics? Do you remember we had a big 9? This is one of our big 9s. So this is benzene with a carboxylic acid. So how do I name this? Benzoic acid. Big 9, you should remember that. So now I have a side chain, all right, and now what? Well, interesting. So how am I going to do this? Well, do you recognize that, as a matter of fact? That's toluene. So this is, in a sense, going to be toluic acid. All right. So this is aromatic acid named by attaching the suffix oic or ic acid to an appropriate prefix derived from the aromatic hydrocarbon. So that's your toluene. So this is, well, what's the relationship? Ortho toluic acid. Now, I'm not sure, but I don't know why you couldn't do ortho methyl benzoic acid. All right, I'd have to look that one up. I don't see really what's wrong with that one, but I think the toluic acid is a little bit more widely accepted. Okay, and let's go on to the next page.